floor is yours.
Okay. Yeah, I'm Gabe Kapchuk. I'm at Boston University. This is a paper titled Order C MPC for Highly Repetitive Circuits. This is joint work with my co-authors, Gabby Beck, Arisha Goel, and Abhishek Jain from Johns Hopkins University. Over the past many years, we've seen a lot of really impressive and efficient results in secure multi-party computation that have resulted in a number of protocols that are actually efficient enough to instantiate and run and have real applications. In general, these protocols all have order n times c total computation and communication complexity. And what are these things? N is the number of parties that participate in the protocol, and C is the circuit. And so we say, the size of C is the size of the circuit. And in general, right, if you have n times c total work, that means that each party is doing about order C work. And as C gets really large, the total computation that each party has to do starts to become too cumbersome. And this ultimately limits the number of the kinds of parties who can actually participate in the protocol. And so the main focus of our work is seeing, is it possible to do better than order NC? And there's been a little bit of prior work in this area. So there's a series of works that get O tilde C total communication and computation complexity, and they're able to do this for general circuits. But the tilde here hides a polynomial factor in log C and also in the security parameter. And ultimately, this results in a not concretely efficient scheme that's never been implemented and never been used in practice. Additionally, there are some works that also achieve order C MPC, but they're only work for a small subset of circuits, a small class called Cimd circuits, which I'll quickly give you a picture of right now. So Cimd circuits are where you have one part of the circuit which has arbitrary topology and arbitrary gates, and then that same mini subcircuit is repeated many, many times in parallel. And in general, in order to get order C MPC, you need this kind of parallelism where there are about order n parallel copies of the circuit being run at the same time. And it turns out that although these protocols are actually quite efficient to instantiate, nobody's actually implemented them or run them on anything, maybe because simple Cimd circuits are not sufficiently interesting in practice. So the main question in our work is, can we design an order C MPC protocol for a larger and more interesting class of circuits? So our contributions is that we give a order C MPC protocol for a class of circuits and functionalities we call highly repetitive circuits, which I'll give you a flavor of in just a moment. And our protocol, we give both a semi-honest and maliciously secure version, and it is secure against T is less than n by 2 minus a little bit static corruptions, or that little bit is a performance parameter that you can tune. We achieve information theoretic security with no security setup, no setup assumption, sorry. And security with abort. What's really nice about our protocol is that when you have order C MPC, you naturally get a sort of division of labor property, right? The total amount of work you're doing is kind of independent of the number of parties. So as the number of parties increase, the amount of work each party does actually decreases. And this is a really lovely property. Our protocol is actually concretely efficient, and we implemented it and show that it is competitive with modern protocols for even small numbers of parties, but begins to outclass them as the number of parties grow. So just to quickly give you a flavor for what these highly repetitive circuits are, we kind of start out by giving a notion of an AB repetitive circuit, where an AB repetitive circuit is composed of an arbitrary number of blocks of width A, each of which recurs at least B times throughout the circuit. Right, so in the case of this circuit here, there's a particular block highlighted in red here that shows up 3 different times, kind of distributed throughout the overall circuit. And similarly, here's a green block that recurs 3 times and a blue block as well. And so overall, this example circuit that I have here is a 3-3 repetitive circuit. A highly repetitive circuit we say that an AB repetitive circuit is highly repetitive with respect to n parties if both A and B scale with n. We find that there are actually a lot of different useful and interesting applications that fit within this class, including stuff like for loops and while loops that kind of have sequential repetition, along with machine learning training algorithms and cryptographic operations that have many repetitions, like block ciphers and cryptographic hash functions. I just want to quickly give you an idea of the flavor for how we actually achieve our results. And I'm going to start by kind of going over the basic O tilde C or order C template from prior work. So what you do is you start out with an existing efficient multiplication subprotocol. So for instance, the multiplication protocol in DNO7. And to quickly recap how this works, the players are given correlated randomness with shares of random values R with respect to both degree T and degree 2T sharings. And the multiplication subprotocol has players locally multiply their shares. They then mask using the degree 2T share of the randomness, and everybody sends their shares to a single player, often called the leader, who will then reconstruct the value and send it back out. And then players will kind of unmask the received value using their degree T shares. They then combine this this multiplication subprotocol with a pack secret sharing scheme. And for those who are not familiar, pack secret sharing is kind of a vectorized version of Shamir secret sharing, where you're able to apply the same operation to many elements all at the same time. And in general, you're able to put order n elements inside this vector and operate on them simultaneously. And so this has been the general template that prior work has used in order to get below order NC. So we follow the same basic paradigm in order to achieve our result. In particular, we start with the same NC multiplication protocol, but then we kind of make conceptual changes to pack secret sharing that allow us to accommodate greater variations in structure throughout the circuit. And in particular, there's two notions. So the first is differing operation pack secret sharing. Escape the blue box. So the idea of differing operation pack secret sharing is that you're able to use different operations as you kind of either multiply or add these two vectors together. So in the first element, you might add, and the second element, you might multiply, and so on and so forth. In practice, we realize this by just actually performing both operations. And then because the leader is able to see all of the reconstructed values, they're able to select the particular values that they want and then share that back out. In order to make this work out, we do need some kind of special correlated randomness in order to get the masking to work properly. Additionally, we also have a realignment procedure for pack secret sharing schemes. The idea is that with a realignment procedure, you're able to kind of permute the order of items both within a single vector and between vectors. And again, the main trick here is that you have the leader who actually sees all of the reconstructed values do this permutation on their own. And again, in order to get the unmasking to work, you need a kind of special correlated randomness. So putting these two things together, this multiplication subprotocol, along with a pack secret sharing scheme, you end up with an order CMPC protocol for highly repetitive circuits. And in particular, the reason it only works for highly repetitive circuits is that in order to do this special correlated randomness generation, you also do it in order C time, order C complexity. And in order to do that, you need a sufficient amount of repeated structure in order to amortize over that structure. And so just to state the result again, so we achieve order CMPC for highly repetitive circuits. There's also some additional fun stuff in the paper, like a non-interactive share conversion protocol, and also how to achieve malicious security in this setting. And if you're interested, please check out the paper on ePrint and the video that Arushi recorded as well. Thanks very much.
Yes, thank you for a nice delivery talk. Any questions in the room? From the audience here? Online, apparently none. Yeah, you also answered my questions along the way during the talk. All the answers came by, so let's thank the speaker again. And we move on to the second talk. Fourth talk, the fifth speaker will be in the room again. Okay, after I think. All right, so I think Arkady Yerukimovic is all set. We have to stop sharing the screen also. So the title will appear in a few seconds. The more, the merrier, reducing the cost of large-scale MPC.
We see it. You don't need to stop sharing. That's okay.
Okay, great.
Okay, then we will.
Okay, thank you very much for the introduction. My name is Arkady Yerukimovic, and today I'm going to tell you the paper titled "The More the Merrier: Reducing the Cost for Large-Scale MPC," and this is joint work with Dov Gordon from George Mason University and Daniel Stern from Peraton Labs. So, MPC research has now been in existence for over 30 years. But still, most of the truly practical MPC protocols are really optimized for small numbers of parties, things 2, 3, 4 parties. And one of the reasons for this, as Gabe actually already mentioned in the previous talk, is that a lot of our protocols, the cost doesn't actually decrease as we add more parties. As we add more parties, oftentimes the cost, even per party cost, actually increases as we add more parties. And so for this reason, there's not really an incentive for parties to join our MPC protocols. And so sorry, can you hear me? Oh. And our goal in this talk is to build large-scale MPC with diminishing per party costs, right? So we want that as we add more parties to the protocol, the cost for each party decreases. And as Gabe mentioned, we're not the first people to look into this line of work. And in particular, there's a good amount of work on sublinear MPC. And what sublinear MPC means is where the total cost across all the parties grows sublinearly in the number of parties. And there's two general directions that sort of follow this approach. The first one of these is what's known as Cimd computation, where the idea is that you pack your values into vectors and you operate on those vectors sort of component-wise in parallel.
Sorry, Arkady?
Yeah, can you not hear me?
Yeah, so we had a problem showing your slides on the local screen here in home. So could you please start again?
Okay. Can you see them now? Or?
Just use the time you've practiced now. You warmed up. So I
okay.
hope.
Can you see my slides? I just want to make sure that you can see them now. Can you see my slides now?
We also your slides were visible online for everybody on Zoom, but not in the room. So now it's fixed, and please go ahead.
Okay, thank you. So again, my name is Arkady Yurkimovich. The paper is entitled "The More the Merrier: Reducing the Cost of Large-Scale MPC," and this is joint work with Dov Gordon from George Mason University and Daniel Sterin from Paraton Labs. So MPC research has been around for over 30 years at this point, but still at this point, most of the truly practical MPC protocols are really focused on the setting for small numbers of parties, think like 2, 3, or 4 parties. And a primary reason for this is that in most of our MPC protocols, as we add more parties, the per party cost does not decrease, and oftentimes it actually increases. And of course, this means that there's no incentive to add more parties into your protocol. And sort of to change this, we looked into how do we build large-scale MPC where the per party cost actually decreases as we add more parties into our protocol. So we're not the first ones to look into this. In particular, there's a fairly substantial line of work on sublinear MPC, where the idea is to have the total cost of the computation grow sublinearly in the number of parties. And there are two general approaches that kind of all works in this area take. The first one that Gabe already described so nicely in the previous talk is following Cimd computation, where the idea is that instead of computing on individual values, you compute on vectors of values pointwise, where the cost of vector operations is small. And this is very nice. It allows us to get low cost, but there's some overhead for evaluating non-Cimd circuits. Another approach for getting sublinear MPC is actually committee-based MPC, where the idea is that instead of running your MPC protocol on all n parties, you elect a small committee of some size and have that committee essentially run the protocol for you. And so you get low average cost, but on the other hand, the committee members still have to do a lot of work. And our paper is really going to combine these two approaches in sort of a way to get optimal cost for both settings. So specifically, our result, we shows that assuming a secure PRG, there exists a maliciously secure MPC protocol that secure against the adversary corrupting at most serves of parties against that achieves security with a board, where the cost of both communication cost and computation cost decreases as more parties are added. And in particular, if you compare this to sort of existing solutions based on these two approaches I mentioned earlier, the best Cimd-based solution is actually O of log C times worse because of issues of having to sort of transform the circuit into a Cimd circuit. And the best committee-based solutions are actually O of S times worse, where S is, in fact, a statistical security parameter. So how do we work? I want to very quickly kind of run through a protocol to explain how it works. And the first thing we do is this. We observe, like most of the efficient MPC protocols nowadays, our protocol is going to start by building Beaver multiplication triples. And these are just random values, A, B, and C, such that C equals A times B. And the observation we make is that So multiplication triple generation itself is actually a nice Cimd circuit, because of course all you have to do is take each A, multiply it by each B to get each C. And so we can generate all of these in parallel, in particular in a component-wise fashion. So what we do is we start out by building packed triples, where we have packed parties share packed random values A, packed random values B, and multiplies these to produce packed random values C. We do this using a variant of the Damgard-Nielsen protocol that Gabe also described earlier. And the idea is that we can actually pack O of n values into each vector and produce sort of O(n) triples, packed triples, using each multiplication. Now, there is a little bit of a caveat that actually just using packed sharing with Damgard-Nielsen doesn't quite work. We have to do a little additional work to prevent a linear attack. And if you want to know about that, there's a description in the paper. But the point is that in the end, we get per party communication O of n to produce O of n squared encoded triples. Now we have these Cimd triples, but of course the question is, how do we use them, right? The problem is that we said we want to do general computation. We don't want to do Cimd computation, and yet what we now have are Cimd triples. And our observation is that you can actually unpack these triples at low cost by turning to the committee-based approach. So now what we're going to do is, instead of using the triples directly, we're going to unpack them. And to do that, we're going to create a large number, specifically O n over S, of unpacking committees. And these committees are going to be small. In particular, the only thing we're going to use in these committees is that there's at least one honest party in each committee. And of course, the question is now, how do you possibly use packed secret sharing in these committees? There's not enough parties to reconstruct the packed secret sharing inside of each committee. And the trick we find is this. So what we do is we have each of the original n parties that holds a share of the packed secret sharing will additively subshare their share to the unpacking committees. So in the end, each unpacking committee holds now an additive sharing of the full packed secret sharing. And it turns out that you can actually unpack this, that the process of unpacking a packed secret sharing just consists of linear operations. And so the unpacking committee parties can just do this underneath the additive secret sharing without revealing anything and extract out the unpacked triples A, B, and C. Of course, once we have the unpacked triples, we can just use sort of standard techniques to achieve the online phase order protocol. And specifically, because we're now working in the dishonest majority setting, we're going to use the speeds protocol. So the first thing we're going to do is actually authenticate those triples. We do this kind of the same way that speeds does it, by sacrificing some of the triples to produce authenticated triples. And once we have authenticated triples, we can just use the standard speeds protocol inside of each committee. And the important thing is, because we have many committees, each committee can be responsible for a small fraction of the gates. And so even though the cost of speeds is sort of each party does constant communication per gate, the number of gates that each party has to do is small, allowing us to get this cost low. So to quickly summarize the costs, we have the following steps. We have triple generation, we have the unpacking, and the online phase. So for triple generation, the basic cost is this cost of the Damgard-Nielsen protocol, which requires C over n communication. On the computation side, there's additional log n factor due to having to interpolate the polynomials for the packed secret sharing. In the unpacking triple steps, the actual dominant cost from communication is in sending the shares to the unpacking committees. And we show how you can do this with total of C over n communication as well per party. So total offline communication complexity is O of C over n. And the computational cost is SC log n over n. And then the online phase now, because we only have each party in a single committee, computing a small fraction of the gates is also now S over n times the size of the circuit. And this gives us the claimed results that we claimed. And finally, like Gabe, we also implemented this and evaluated how it costs. And we see that as the number of parties grows, the cost for generating authenticated triples, which are the things that you need for the online phase, really does decrease with the number of parties. So specifically, we showed that once you get up to 2 to the 20th parties, we can generate 1 million authenticated triples in about 10 milliseconds. And so hopefully, what it convinced you here is that this protocol really is decreasing as and increases, and thus the more the merrier. Thank you.
Yeah, thanks. Any questions from the room? So on one of the last slides, you actually showed that you ran this protocol with 1 million parties.
Yeah, so I have to be correct. So we computed the computation cost of the party. We couldn't actually run the full protocol because, of course, we don't have access to a 1 million party network. So we sort of emulated the communication part and actually computed the computation costs to give the total running time.
Okay, so those were estimates.
Yeah, yeah.
Would be nice to run the real experiment then, but maybe it's any more questions? No. Okay, let's thank the speakers again. Let me move on to the talk by Ilan Komargotsky. The next talk. Okay, yeah, this slide is already showing. The talk will be about multi-party, reusable, non-interactive, secure computation. Ilan, please go ahead.
Can you hear me? Okay, so the talk is about non-interactive, secure multi-party computation from LWE. I'm Ilan Komargotsky, and this is based on joint work with Fabrice Ben-Hamouda, Ayush Jain, and Rachel Lim. So the motivating scenario for our talk is a strong version of standard secure computation. So imagine the following setting. There are 3 hospitals, each having their own private database. So hospital number 1 has X1, hospital number 2 has X2, and hospital number 3 has X3. We want to be able to implement the following secure computation protocol. We first want each player to be able to commit to its own input and publish this commitment on a public bulletin board. And then, at a later stage, these 3 parties may want to jointly perform some computation on their joint inputs. So compute some function f on x1, x2, and x3. We want to be able to compute this function by sending just one single message from each hospital to some public evaluator. And that public evaluator will be able to compute based on these 3 public messages, along with the public commitments to the inputs, the function f that it wanted to compute. So this is sort of a version of 2-round MPC, but we want to do a little bit more. So we want to allow, for instance, for somebody that comes later to join the computation at a later stage. Let's say it's a hospital number 4 that has private input X4, and then it will commit to its input, publish it on the public bulletin board, and later, let's say, want to compute some function together with party number 1. They will be able to do it by sending just one single message from each party to a public evaluator that will allow him to compute the function f prime on x1, x4. So this is the motivating scenario for MRNISK, and this is what MRNISK basically is. Slightly more formally, an MRNISK is a secure computation protocol with 3 phases, 2 of which consist of interaction, and the last is just an output phase. So in the first phase, whenever a party joins the system and wants to participate in the secure computation, it commits to its private input and remembers for itself some private state. So X hat is the encoding or the commitment to the input, and S is the secret state that it keeps for itself. Then any subset of parties might want to compute a function f together with all of the known public encodings of some subset of parties and the secret state of only that party. It can encode the message alpha, and then all of the alphas together with the encodings of the private inputs of the corresponding parties it should be possible to publicly compute the output of the functionality. So this is a very simple communication pattern for secure computation. And importantly, we want correctness even if parties join dynamically. So as long as the computation proceeds, even perhaps after some of the parties already performed some computations. And in terms of security, in this work, we focus on semi-honest or semi-malicious security. We assume corruptions are static and the dishonest majority. So this is the formal syntax of MRNISK. And in other words, you can just think of MRNISK as a very strong version of two-round MPC, where the first message is reusable across different second message computations. And the set of parties that participate in the game is completely dynamic. Namely, parties can join along the way. And this also implies that the first round message, for example, has to be very short and independent of the number of parties. So this is a very simple way to think of MRNISK. What do we know about this very strong and powerful definition of MPC or communication pattern for MPC? So we have a handful of constructions, some of which achieve this communication pattern and some of them don't. So the early constructions of two-round MPC can actually be shown to satisfy this very strong notion. But the problem is that they're based on I/O or witness encryption, which, although we know how to base them on well-established assumptions, they're still very inefficient, and they're based on still based on a collection of assumptions. And we want a protocol that's based on a single clean assumption. The second generation of constructions, which use the multi-key FHE or homomorphic secret sharing, they do not satisfy the properties of MRNISK. They don't support the dynamic set of parties, namely the first round messages. For instance, the length of the first round message of each party depends on the number of parties. And this concept of MRNISK was introduced about a year or a year and a half ago by Ben Hamouda and Lin in TCC, where they showed the first construction based on SXDH, so pairings, groups with pairings. And in this work, and also in the next talk, we construct an MRNISK based on LWE. That's the main result. So in a very high level, the way we achieve our construction is the following. We identify a complete functionality or a complete primitive, which if we build it, then you can generically compile it to get an MRNISK. We call this primitive reusable functional OT. And this is, you can view it as an extension of standard OT that suffices to be compiled into this very strong MRNISK. And the technical contribution is a construction of this reusable functional OT from LWE. And together we get the construction of MRNISK from LWE. We observed that MRNISK has applications or interesting applications by itself to classical cryptographic primitives. For instance, we show that you can take any multi-key FHE scheme and then take the decryption phase and make it and use an MRNISK to implement it. And this directly gives you a threshold multi-key FHE scheme. And if you just run this compiler, you get a construction with better parameters than what was known. So this is very nice. And the way we implement it is as follows. So let me tell you what a functional OT is, and then I'll tell you a couple of words about how we build it. So a reusable functional OT is just a special case of MRNISK. So it's a special functionality, it's a special case that only concerns two parties. So there's only Alice and Bob. Alice's input is called X1, Bob's input is called X2, and the function that we compute looks as follows. We're given two functions, G1 and G2. We apply G1 on X1. G1 gives us two inputs, two outputs, L0 and L1. You can think of them as labels of a garbled circuit. And G2 is applied on X2 and gives us a bit. And what we want is to get the L sub bit label. This is a very natural generalization of standard OT, sort of a functional version of OT where also the commitment to X1 and X2 are going to be reusable with many G1s and G2s. And the way we construct it is based on, we start with just using a homomorphic commitment for X1 and X2. And then the online phase is implemented using a very nice idea of Brokersky and Dotling from a couple of years ago, who constructed a statistical sender, a two-round statistical sender OT. So I refer you to the full version of the talk or the paper for more details about this. So just to conclude, we identify the complete primitive for MRNISK. If you build it from other assumptions, you would get an MRNISK from other assumptions. Maybe perhaps the most interesting open problem is to build it from DDH or even just OT. So this is an open problem. And just as a note, we have a new manuscript on ePrint together with Rex Fernando and Ayush Jain, where we construct a maliciously secure MRNISK, which satisfies super polynomial simulation. So see ePrint if you're interested, and thank you very much.
Thank you. Time for quick question, very quick question. Don't think. No, so then in the interest of time, let me move on to the next talk. Let's thank the speaker again. Thanks, Kenan. So Chen Jung Yin, yes, will be our next speaker with a talk entitled Unbounded Multiparty Computation from Learning with Errors.
Hello, can you hear me?
Yeah, we hear you. Please go ahead.
Yeah, thanks for the introduction. So as you may already know, so this work is the concurrent work with the previous presentation. And in this work, we also study the dream version of two-round MPC protocol. So for such a dream version of protocol, recall that it should satisfy these following properties. It should be in the plan model, and the first round message should be reusable for different functions. And we require that any party, and we require that the first round message should satisfy the unbounded parties property, where the number of parties is not bounded by the first round messages. And any subset of parties can jointly compute some function f in the second round. And in this work, we call this MPC protocol as an unbounded MPC. And such a notion was subsumed by the previous work of Mahmoud and Lin, and they call this notion as Mr. NISK. So previously, as you may already know, for the previous works, for MPC protocols of two rounds with the reusable first round message, they are either in the CRS model or don't satisfy the unbounded parties property or the ad hoc computation property. And the exception is by the previous work of Mahmoud and Lin, where they achieve all the properties, but their assumptions is from bilinear maps. So, but the bilinear maps are not post-quantum secure. So in this work, we study the following question. Can we construct the unbounded MPC from learning with arrows? And here is our result. We construct a two-round semi-malicious unbounded MPC in the plan model from learning with arrow. As you already know, there is also a concurrent work by the last talk. They also construct Mr. NISK from learning with arrows. So to obtain our result, our key ingredient is the following attribute-based secure function evaluation with public decryption property. Such a primitive is a two-party protocol between a sender and an authority, where the authority holds some policy P, then it encodes this policy P as some public key and send it to the sender. So the sender can use this public key to encrypt some message M with some attribute and compute some ciphertext. Then on the authority side, he can also use this same attribute to generate some hint H. Then we require that anyone with the ciphertext and the hint can publicly decrypt this message M if the attribute is satisfied by this policy. On the other hand, if the attribute is not satisfied by this policy, we will require that this message M is hidden from the authority. And on the authority side, we request that the public key and the hint should reveal nothing else beyond the information about whether such attribute is satisfied by this policy or not, and it should hide everything else about this policy. So in this work, we construct such ABSFE with a public decryption property from learning with arrow, and then we combine it generically with two-round MPC protocol to obtain these unbounded MPC protocols. Thank you. For more information, you can see our full paper online.
Yes, thanks.
Yeah,
Thanks, Owen.
thanks.
Yeah, we have surely some time for questions. Online, no. Oh, so this all belongs to a class of multi-party computation where you limit the interaction also, eh? like in the previous talk.
Yeah, yeah. It's the notion is the same as the previous work, the previous presentation.
Yeah. And where does the unbounded in the title refer to? Because I actually missed that point. So unbounded multi-party computation, and unbounded in which sense?
Yeah. So let me. Yeah. So for unbounded we mean. Oh. Yeah. So for unbounded we mean we require the first round message not bounded the number of parties. So so for some MPC protocols is after the first round message, the number of parties can be involved for the second round is already bounded. But we require after the first round message, the number of parties can be involved in the second round is unbounded.
Okay, yeah, thanks. Yeah, I missed the very first part of your talk here. Yeah. A question? Okay.
So once you say that you have unbounded parties, this new party
Well, you cannot.
So thank you. So once you say that you have unbounded parties, can this new party inject new secret to this computation? I mean, let's say we have updatable parameters that we can update with new party which comes to this computation.
Yeah, we allow new parties to join.
Yes or no?
Yes.
Okay, thanks. Yeah.
Okay, thanks. Any more questions coming up? No? Okay, then let's thank the speaker again.
Thank you.
We will have our next speaker here with us in the room. David is coming up. Oh, the Pope. Yeah. Yes, one of these.
Yeah.
Yeah, that's fine. Okay. You have to share the full screen. Full screen. I can't see the most, to be honest. So we're on time, so no problem. Ja. Ist so ein Web-Screenshot? Kann das der Inhalt erstellen? Kannst du da kurz? This one?
You'll need to go under display settings and swap the presenter view.
I think
we can also share. So let's share. And then we can share this one. Yeah. But then next talk, you have to watch out again.
Yeah, you have to get rid
Yeah,
of
please go ahead.
Okay, hello everyone. My name is David Kratzler, and today I present a paper of ours called a generic compiler for publicly verifiable covert multi-party computation, or PVC-MPC for short. This is a joint work with Sebastian Faust, Kamit Hassai, and Benjamin Schlosser. Yeah, okay. Yeah, so I guess you're all familiar with semi-honest security and malicious security. And in between, there is covert security, in which an adversary is allowed to act arbitrarily as in malicious security. However, the adversary even has a chance to break the security guarantees by cheating. On the other hand, the honest parties have a chance to detect the cheating attempt and thus identify the adversary, which kind of harms its reputation. There's an extension which is called publicly verifiable covert security, in which honest parties that detect cheating can also generate a proof of misbehavior, which can be transferred to any third party to convince this party about a cheating attempt. So previous work mainly focused on the two-party setting for PVC MPC, while we want to focus on the multi-party setting. In particular, we present a compiler which transforms any semi-honest secure protocol into a PVC one. So let me give you a short overview of our contribution. So we have the just explained compiler, and this means that we are the first to formally specify and prove a PVC MPC protocol. There has been prior work which presented kind of an intuition on how to extend the two-party approach to the multi-party setting. However, in this prior work, the detection probability was bounded by 1 over the number of parties, while we do not have something like this. And when I say we are the first, I want to mention that there's also concurrent work with similar techniques than ours and also similar results. Yeah. Besides our major contribution, we also are the first to incorporate time lock puzzles into a simulation-based security proof, and we specify verifiable time lock puzzles. I will focus on the first part, the compiler. So I want to give you a short overview or a simplified overview of our compiler. We will focus on the offline-online setting, in which there is an input-independent offline protocol and an input-dependent online protocol. Actually, we do not have to do anything with the online protocol because it's typically fast anyway, and we just take a malicious secure online protocol. However, with the offline protocol, we need to do some changes, and we take a semi-honest offline protocol and we de-randomize it, which means that parties derive all of their randomness from some predefined seeds. And also we add some kind of public transcript. So yeah, now we have two parties and both of them have some secret and some random seeds. And then they execute two instances of this semi-honest protocol in which they get out some transcripts together with some pre-computations. Next, these parties execute a malicious secure MPC protocol in which they insert a coin share together with their seeds. And this malicious secure MPC protocol then adds up this coin shares to a coin and puts the coin together with the corresponding seeds into a time lock puzzle, which is then given to the parties. Next, the parties sign the transcripts together with the time lock puzzles, but at this point, no party really knows what is inside the time lock puzzle, so they do not know which instance is actually opened and which instance will not be opened. Then in some second round output phase, the malicious secure MPC protocol just gives what is inside the puzzle to the parties. This way, parties do not really have to open puzzles in the optimistic case. However, in the pessimistic case, when a rushing adversary that learns the second round output first aborts, parties can simply open the time lock puzzle and still get whatever is locked inside. In the next step, any party can emulate the protocol because it has the seeds now of this protocol instance, and then just emulate it locally and compare the resulting transcript to the transcript of the real execution. Now, if the transcripts are not the same, obviously there is some cheating. Otherwise, the parties can just continue with the online phase. If there's cheating, parties can just publish the transcripts, the signature, and the time lock puzzle, which is sufficient for any third party to also emulate the protocol and detect the cheating attempt. If they continue with the online phase, they cannot use the pre-computation of the open instance, for example, instance 1, which this means that this pre-computation goes to the trash. However, they can use the other pre-computation in an online phase in which they then use the actual secret inputs and get the final outputs. The cool thing here is that the complexity of this malicious secure protocol is independent of the overall protocol, which means that it doesn't matter if parties generate like 10 or 10,000 of pre-attributes. This puzzle generation just costs the same, which means that the cost of this puzzle generation amortizes over the complexity of the semi-honest instances. And if we have several instances, let's say T instances, then all but one of these instances can be opened, which means that the detection probability is T minus 1 divided by T, which is actually was like our goal, because we wanted to decouple the deterrence factor or the detection probability from the number of parties. This already concludes my talk, and thanks a lot for your attention.
Yeah, thanks, David. Any questions in the room? Online? No. Yeah, no, it was nice to see that you use a. Oh, there's a question from someone else. Get you the mic.
Thanks for the talk. You said you could have like an arbitrary detection factor, or did I miss here? Like now you said like it was t minus 1 over t.
Yes, like you can pick any t and you always achieve t minus 1 divided by t, while this intuition of the prior work was bounded by 1 over n, so you could not get better than 1 over n, at least not without doing some additional complex stuff like repeating the protocol.
But t still depends on the number of parties, right? It's not arbitrary.
No, t is the number of instances that are executed.
Ah, okay, thank you.
Another question.
Can you also get MPC with identifiable abort from this approach?
I guess adding identifiable abort is kind of orthogonal. So if you aim for a publicly identifiable abort, I do not know if this is not sufficient. I guess you will need something like a blockchain or something like this and just put the messages on the blockchain. And for a normal identifiable abort, I think like in the original notion of PVC and covert security, they have something like identifiable abort directly in the notion, which is typically like relaxed and people typically do not aim for this. And therefore you would need something like broadcast.
Thank you.
You're welcome.
Okay, then. Well, that's it. Let's thank David again.
Thanks.
So we set things up for the final talk for this session, not for today. We have a rum session tonight. Jifan Song is our last speaker online. Hetzelfde probleem. Oh ja, dat is ook een truc. Ja. Yes. So, Jifan, you're all set?
Yeah.
Yeah. So please, yeah, your talk, constant overhead, unconditionally secure multiparty computation over binary fields. Please start.
Okay. Hello, everyone. My name is Yifan Sang. Today, I'm going to introduce my recent work, constant overhead, unconditionally secure multiparty computation over binary fields, co-authored with Antigone Polychroniado. Multiparty computation allows several mutually disjointed parties to evaluate the function on their private inputs. It guarantees that protocol execution does not leak any information about the individual inputs beyond what can be inferred from the function output. Usually, the functionality is represented as an arithmetic circuit over a finite field, and the circuit supports addition and multiplication operations. In this work, we focus on small fields, such as the binary field. We focus on the information theoretic setting with Einstein majority and assume a P2P channel between every pair of parties. We are interested in the malicious security with the board. In the following, I will use N for the number of parties and T for the number of corrupted parties. No solutions to the information theoretic MPC protocols all have a log and multiplicative overhead in the communication complexity. Concretely, the communication cost per gate is order of n times log n bits for small fields. This is because most of the communication efficient MPC protocols are based on the Shamir secret sharing scheme. A Shamir secret sharing naturally requires a large finite field of size at least n, which leads to the log n multiplicative overhead. Two recent works also studied the suboptimal threshold, where the number of corrupted parties is bounded by 1/2 minus epsilon times n. They both achieve order of n bits per gate, but relying on two different techniques. However, we would like to point out that their solutions do not extend to the standard INS majority setting. Also, a recent crypto work, GPS21, shows that one can even achieve out of log n bits per gate in the suboptimal threshold. In this work, we studied the following question. Is it possible to construct information theoretic MPC protocols in the standard INS majority setting for computing a single Boolean circuit with amortized communication complexity out of n bits per gate? Our work answers this question affirmatively. We show that there is an information theoretic MPC protocol in our setting which achieves an amortized communication complexity of out of n bits per gate. Our result can be naturally extended to any finite field with communication complexity out of n elements per gate. Our starting point is two protocols in different settings. The first one is the speech-like protocol. In the designed majority setting, it is known that information theoretic protocols are possible in the preprocessing model. The well-known speech-like protocols can achieve out of n bits per gate, but require to prepare out of n times kappa bits of preprocessing data. Here, kappa is the security parameter. The main technique is to use additive sharings with information theoretic max. Preparing such amounts of preprocessed data in the INS majority setting requires out of n times kappa bits of communication. The second one is the protocol in CCXY18. When targeting for Cimd circuits, that is, evaluating multiple copies of the same circuit, the protocol in CCXY18 shows that one can evaluate log n copies of the same circuit such that the communication cost per gate is out of n bits. The main technique is the notion of reverse multiplication friendly embeddings, or RMFE for short. It allows us to perform coordinate-wise multiplication over small fields by only operating on the extension fields. Unfortunately, their solution does not work for single circuits. Our idea is to use the protocol in CCXY18 to prepare the preprocessing data, which is used in an efficient speech-like online protocol. Our reason of doing so is that usually the preprocessing data is much easier to be prepared in a batch way, since we do not need to consider the circuit structure. The main difficulty is that the preprocessing data prepared by the protocol in CCXY18 should be used to evaluate the batch of gates each time. However, if we want to use a speech-like online protocol, we need to unpack the preprocessing data so that they can be used gate by gate. To achieve that, we introduce what we refer to as hidden additive secret sharing. Due to the time limits, I will just give a high-level overview of our approach. In CCX18, a RMFE is a pair of linear maps phi and psi. The sharings prepared in CCX18 are in the form of degree T Shamir sharings of phi A, where A is a vector of k bits. To use a speech-like online protocol, we define the MAC part as follows. For an additive sharing X, the MAC of X is a degree T Shamir sharing of Y, and the vector psi Y satisfies that the summation of all entries is X. Here, psi is the second linear map in the RMFE. We show that we can locally transform a degree T Shamir sharing of phi A to k additive sharings with their corresponding max. These sharings can then be used in the speech-like online protocol. Of course, there are also other issues. For example, we need an efficient verification protocol to achieve malicious security. More details about our technique and protocol can be found in the full video and our paper. Thank you.
Yeah, again. So, any questions here in the room? No, online? No. So maybe one question. So this is ON, number of parties.
Yes.
Yeah. So is it also practical for a small number of parties? So or does the result kick in when the parties go to infinity, or as a total result?
Yeah, it's for any number of parties. But I mean, if n is a constant, actually maybe you can just use the protocol with complexity n log n, which is still a constant.
Yeah, because then, yeah, maybe then the constant overhead for constant is maybe not so interesting too. Yeah. All right. So with that, I think it's time to thank Ivan again and thank all the speakers. Not all the speakers of today yet. So we have this RAM session coming up at 7. I guess also in this room. Where else?